If you hold back 1,000,000 tons of water with a single concrete wall and then suddenly remove that barrier, the result is not just a flood. It is a mathematical nightmare called a dam break wave, a phenomenon so complex that for centuries it resisted every attempt at a perfect physical description. This isn't just about water flowing downhill. It is about a singular moment where potential energy instantly converts into a chaotic, turbulent wall of force that follows rules entirely different from a standard river or crashing ocean wave. When a dam fails, the water doesn't simply pour out. It undergoes a process of catastrophic decompression, forming a wavefront that can travel faster than the water particles themselves, creating a scouring force capable of erasing entire cities from the map in minutes. To understand why this happens, we have to look past the surface-level destruction and examine the fluid mechanics of chaos, where gravity, friction, and the sheer weight of vertical water columns collide in a sequence of events that still challenges our best supercomputers. The history of analyzing these waves began not with a disaster, but with a piece of pure mathematical theory in the mid-19th century. Adhemar Jean-Claude Barré de Saint-Venant, a French mathematician, was the first to derive the equations that describe how a body of water behaves when its depth and velocity change rapidly. His work laid the groundwork for what we now call shallow water equations. Even Saint-Venant couldn't fully account for the instantaneous removal of a dam. He assumed the water would remain a continuous, smooth surface. In reality, the moment the barrier vanishes, a negative wave or a rarefaction wave travels backward into the reservoir, signaling to the resting water that the exit is open. A positive surge wave barrels forward. The physics of this split-second transition is almost impossible to model because the water at the bottom of the dam is under immense pressure, while the water at the top is essentially in freefall. This vertical pressure gradient creates a vertical acceleration that defies the standard horizontal focus of fluid dynamics. To visualize the sheer scale of the energy involved, consider the 1976 failure of the Teton Dam in Idaho. When the earthen structure collapsed, it wasn't just a leak. A wall of water, 60 feet high, roared through the canyon. In a standard river, water moves because of a constant slope. In a dam break scenario, the slope is effectively infinite for 1 microsecond. This creates a phenomenon known as a bore. Unlike a wave on a beach that rolls over and breaks, a bore is a self-sustaining wall of turbulence. It maintains its shape because the high-velocity water from behind is constantly crashing into the slower, shallower water in front. This creates a hydraulic jump that travels. The kinetic energy isn't dissipated quickly. Instead, it is concentrated at the very front of the wave, which acts like a liquid piston, pushing air and debris ahead of it with the force of a localized hurricane. The complexity of this wave is further deepened by the sheer variety of ways a dam can fail. If a concrete gravity dam tips over, the release of water is different than if an earthen dam erodes from within. In an earthen dam failure, the breaching process is gradual but accelerating. As water overtopped the Teton Dam, it began to carve a small notch. That notch increased the velocity of the water, which increased the rate of erosion, leading to a feedback loop that widened the gap exponentially. This means the dam break wave isn't a single event, but a growing crescendo of force. The hydrograph, which is a graph of water flow over time, shows a peak that occurs much faster than any natural rain-driven flood. In the 1959 Malpasset Dam disaster in France, the wall of water reached the town of Fréjus in 20 minutes, moving at speeds exceeding 18 miles per hour, even after traveling miles from the source. The mechanics here are governed by the friction of the terrain. while the fluid itself is governed by Navier-Stokes equations. The ground it moves over is a chaotic variable. Rocks, trees, and buildings are entrained into the flow, turning the water into a high-density slurry. This increases the moving mass and the momentum, making the wave progressively more destructive as it travels. One of the most counterintuitive aspects of the dam break wave is the difference between the dry bed and wet bed scenarios. If the wave moves into a dry valley, the leading edge is slowed significantly by friction with the ground. This creates a blunt, rounded nose of water and debris. However, if there is already a river or a previous flood layer in the valley, the wave can travel as a sharp, vertical wall known as a shock front. In a wet bed scenario, the resistance is lower because the water is essentially sliding over other water. This allows the surge to maintain its height for much longer distances. Scientists use the Froude number to describe this state. It is a ratio of the flow inertia to the gravitational force. When the Froude number exceeds 1, the flow is supercritical. This means the water is moving faster than the waves that would normally ripple across its surface. In this state, information cannot travel upstream. The water behind the wave has no way of knowing what is in front of it until it hits, leading to the massive, instantaneous impact forces that can snap reinforced concrete bridge piers like twigs. The mathematical modeling of these events requires solving the Riemann problem, a specific type of initial value problem in partial differential equations. Effectively, you are calculating the transition between two stable states of matter, the stationary lake and the rushing torrent. Because the transition is so violent, the math often breaks at the point of the wavefront, resulting in what are called discontinuities or shocks. To bypass this, modern engineers use computational fluid dynamics, which divide the valley into millions of tiny cells. Each cell calculates the mass, momentum, and energy entering and leaving it every millisecond. But even these models struggle with the transition of the water from a liquid state to a polydispersed granular flow as it picks up sediment. At a certain point, the dam break wave stops behaving like water and starts behaving like a debris flow or a landslide. The internal friction of the mud and boulders creates a plug flow where the center of the wave moves as a solid mass, while the edges grind against the valley walls. Consider the 1963 Vajont dam disaster in Italy, which remains one of the most terrifying examples of fluid mechanics in history. The dam itself did not break. Instead, a massive landslide fell into the reservoir. This displaced the water so rapidly that it created an overtopping wave, a mega tsunami that surged over the dam's crest. The water didn't just fall. It was launched. As it descended, 1,000-foot drops into the valley below, the potential energy was so concentrated that the resulting wave stripped the soil down to the bedrock and vaporized structures through sheer atmospheric pressure changes preceding the water. The physics here involved a solitary wave or soliton. Unlike normal waves that spread out and lose height, a soliton can maintain its shape and speed over long distances under specific conditions. The narrow Longarone Valley acted as a waveguide, focusing the energy of the water rather than letting it dissipate. It was a perfect storm of geometry and gravity that defied the expectations of the engineers who built the dam. Another layer of this mystery is the role of turbulence. In a standard laboratory flume, water flows in neat, predictable layers. In a dam break, the Reynolds number, which measures the ratio of inertial forces to viscous forces, skyrockets into the millions. This means the flow is highly turbulent, characterized by eddies and vortices that consume energy in a non-linear fashion. This turbulence is actually what saves some structures. The energy spent creating these microscopic swirls is energy stolen from the forward momentum of the wave. This same turbulence also causes intense cavitation. As the water moves at high velocities over uneven surfaces, the pressure can drop so low that the water literally boils at room temperature. creating tiny vapor bubbles. When these bubbles move into higher pressure areas, they collapse with enough force to pit and erode solid steel. In a dam failure, cavitation can eat away at the remaining structure of the dam, even as it is failing, accelerating the collapse in a way that is notoriously hard to predict. Modern research into the dam break wave has shifted toward the study of urban dam breaks. When a dam fails above a city, the street grid acts as a series of channels and obstructions. This creates a man-made labyrinth that can either dampen the wave through friction or amplify it through the canyon effect. When a wave is forced into a narrow street, its height must increase to conserve mass, a principle known as the continuity equation. This means a 10-foot wave in an open field could become a 30-foot wall when it turns a corner between two skyscrapers. Researchers now use high-speed laser scanning and satellite imagery to create digital twins of cities, simulating how these waves would navigate around every single building. They found that the placement of a single parking garage or a park can radically change the survival rate of an entire neighborhood by redirecting the core momentum of the flow. This highlights that the physics isn't just about the water. It's about the boundary conditions it encounters. We also have to consider the tailwater effect. Most people assume the worst part of a dam break is the initial hit. But as the reservoir empties, the physics shift from a wave-dominated regime to a sediment-dominated one. The vanishing lake leaves behind decades of silt and mud. As the final stages of the break occur, this muck is pulled into the flow. This creates a hyper-concentrated flow that is much denser than water. Because the density is higher, the shear force, the product of mass and acceleration, increases. A house might withstand 20 feet of clean water, but it will be crushed by 10 feet of this high-density slurry. This is why the aftermath of a dam break often looks like a volcanic eruption site. The fluid mechanics of the receding limb of the wave are just as complex and dangerous as the initial surge. One of the most significant breakthroughs in understanding these waves came from studying dam breaks on a different scale, specifically glacial lake outburst floods. In the Himalayas and the Andes, natural dams made of ice and moraine fail frequently. These are natural laboratories for fluid mechanics. Because ice dams can fail via floating, melting, or mechanical fracture, they provide a spectrum of data that man-made dams cannot. Scientists have discovered that in these cases, the temperature of the water plays a critical role. Cold water is more viscous, which changes the internal friction of the wavefront. Furthermore, the presence of ice chunks changes the drag coefficient of the flow. By applying these lessons to civil engineering, we've learned that the temperature and viscosity of a flood can be the difference between a wave that peters out in 5 miles and one that travels 50. Despite all our progress, the dam break wave remains impossible in the sense that no model can perfectly predict the exact path and force of every drop of water. Chaos theory tells us that tiny variations in the initial breach, a few centimeters here or there, can lead to vastly different outcomes miles downstream. This is the butterfly effect, applied to millions of tons of rushing liquid. It is a reminder that while we can build structures to hold back nature, the moment those structures fail, we enter a realm of physics where the variables are too numerous and the forces too great for total human comprehension. The fluid mechanics of a dam break are a testament to the raw power of gravity when it is suddenly unleashed from its cage. Understanding these mechanisms is more than an academic exercise. As the world's dam infrastructure ages, the risk of these chaotic events increases. We are currently seeing a transition from the era of dam building to the era of dam maintenance and removal. Every time a dam is decommissioned, engineers actually perform a controlled dam break. They use the very equations we've discussed to ensure the water is released in a way that doesn't trigger the catastrophic wavefronts of the past. By mastering the math of the surge, the friction of the valley, and the turbulence of the flow, we can turn a potential disaster into a managed process. This knowledge allows us to design better flood defenses, more accurate early warning systems, and more resilient cities. If you found this exploration of high-stakes fluid mechanics fascinating, consider looking into the way we model other planetary-scale fluids, like the movement of magma beneath the Earth's crust or the atmospheric rivers in our sky. The rules of chaos apply to them all. And the more we understand the flow, the better we can prepare for the surge. The physics of a dam break are far more complex than just water moving downhill. When a massive barrier suddenly vanishes, it triggers a unique mathematical event called a dam break wave, a wall of water that behaves like a solid piston, generating forces that defy standard river mechanics. From the rarefaction waves that travel backward into the reservoir, to the supercritical bores that roar through canyons at terrifying speeds, this video explores the fluid mechanics that make these events so destructive. We break down the Saint-Venant equations, the role of the Froude number in supercritical flow, and why a wet bed flood travels faster than a dry bed one. Using historical case studies like the Teton Dam and the Vajont disaster, we examine how turbulence, cavitation, and urban geometry can amplify the power of a surge. Discover how modern computational fluid dynamics and chaos theory are helping engineers predict the unpredictable in an era of aging infrastructure. Hashtag fluid mechanics, hashtag physics, hashtag engineering, hashtag dam break, hashtag civil engineering, hashtag hydrology, hashtag science explained, hashtag mathematics.